So today I was invited here to talk about chaotic terrains on Mars. It's been quite a nice journey because, as you can imagine from the name, chaotic terrains are some very enigmatic terrains on Mars. So it's been challenging, but it's been also fun, and I hope you will enjoy some chaotic terrains with me. Okay, so I dedicated my PhD to chaotic terrains, but not only, also to floor fracture craters that are very similar terrains, and they occur both on Mars and on the Moon. But today we won't talk about that. We will focus just on the Martian part. So basically, I will show you my two works. The first one was characterization and morphostratigraphic mapping of arsenic empiric chaos. And in the second part, I performed an experiment in laboratory to test a new formation mechanism, a caldera collapse. Here you can see the time lapse of the experiment that was successful. And we will see that in detail in a minute. So everything started from the enigmatic chaotic terrains that are these broad regions on Mars characterized by a basaltic bedrock that's been disrupted into polygonal blocks. So here in these two images, you can clearly see the mesas. So we have these flat-topped angular blocks bounded by faults that intersect in each other, form this peculiar polygonal shape. Now, the scientific community agrees on the fact that this disruption was caused by a catastrophic collapse. But the trigger, the primary trigger of this collapse is still debated. Now, I will show you, let's say, the most accepted formation mechanisms that were proposed in literature. The first one was proposed in 2008 by Meresse et al., and it involves an interaction between a magmatic body, such as a sealed dike, and the cryosphere. So we would have the emplacement of this magmatic body that would cause some fracturing in the rocks and a destabilization and melting of the cryosphere. And therefore the water would look for a path to escape, and we would have the outflow and the consequent collapse. The second model is the aquifer model proposed by Harrison and Grimm, and we have this ice cap that is undergoing some cyclic melting, recharging the underlying aquifer up to a point where we have an overpressure in this aquifer, and we have the cryosphere disruption, the outflow, and the formation of chaotic terrains and outflow channels. And then Cargill proposed a clathrate model. So underground, we would have these huge clathrate lenses that would generate a thermal anomaly and then trigger the outflow and all the hydrological processes and the consequent collapse of chaotic terrains. And the last one, proposed by Zegers, involves a buried ice lake. This ice lake would then be covered by new sediments on top of it, up to a maximum overburden, and then the ice lake starts to melt and cause the fracturing and then the outflow and the collapse. So these are the four most accepted models that were proposed in literature. And as you can see, all of them involves water. Just the first one was involving magmatic bodies, but most of them involve water because many chaotic terrains have these outflow channels. And given the size of these outflow channels, one might imagine a huge amount of water. But the reason why I started to question these formation mechanisms was that in some chaotic terrains, like arsenic empiric chaos, the ones that I studied, there are no outflow channels. And in empiric chaos, there are no hydrated minerals at all. So I figured maybe we need a formation mechanism that can explain, the collapse also in these areas where the aqueous evidence is limited and we don't have outflow channels. But there is more to say about chaotic terrains, not just the disrupted bedrock and the polygonal blocks. There are also some units in chaotic terrains that are post-dating this collapse. And they're different in each chaotic terrain. Now here, for example, we have, let me move these around. We have an example from Glotch and Christensen in Aram chaos, the one that you're mapping today. The authors performed a very detailed spectral analysis, and they found out different minerals like hematites associated with sulfates and phyllosilicates. Today we will focus more on the morphostratigraphic properties of these units. But what they proposed is that after the collapse and the formation of the chaotic terrain, we would have a second depositional event with these new units that are not fractured by the collapse. And then with doming and tilting, we arrive to the current configuration, to the current geological setting. And iron chaos was also studied by Lichtenberg et al. In 2010. The authors found two different types of sulfates, mono and polyhydrated. So they hypothesized two different episodes of evaporatic deposition. So this tells us that the geological history of chaotic terrains is quite complex, starting from the collapse that's still debated to the sedimentary deposition that followed the collapse. So there is still a lot to investigate and study in chaotic terrains. Okay, so I started by just observing arsenic and pyrrhic chaos. There are these two chaotic terrains not far from Aram chaos. You can see here it's just a bit southern compared to Aram. And the data that I used are the same data that you're using today. So we have IRIS images, CTX images. There is a software called ISIS3 where you can process this data, apply corrections, and set a map projection, and then you load them on your GIS. You can produce digital elevation models on a software called AIM Stereo Pipeline, ASP, and then you load it on your GIS. And then the last type of data set that I used was the CRISM, the spectral data. And in this case, the software that I used was ENVI. And always the same, you apply first the corrections, and then you start work on your spectrum. And as Beatrice said before, we have different things that we can do, with spectral data. We can first have an idea with the summary parameters. So with this RGB that you can see on the left, and then we can go more in detail with the spectrum. And the first thing that I did was trying and identify the geological units that were described in other chaotic terrains. So by analogy, I wanted to see if in arsenos and pyrrhicas we had the same units. And we had the same units. So we have the chaotic terrain unit, which is the unit of the basaltic bedrock. And it's subdivided into three subunits: the fracture plains, that are the particular mesas that we saw today. And in this left image, you can see that the mesas laterally evolve, almost transitionally, to something more roundish, more eroded, and that's the knobby terrain. So many authors suggest that fracture plains and knobby terrain are actually the same material. It's still the bedrock, but for some reason they had a lateral different evolution and a different erosional evolution. And then the third subunit is the high thermal inertia chaotic terrain subunit. And it's very similar to knobby terrains. So it's still roundish, eroded. You can see it on the right in pink. It's very similar to knobby terrains, but it also presents a higher thermal inertia. And we had all these subunits. So then I moved to the post-collapse units to see if I could find the same units that were found in Aram chaos. Well, what I found was much less complicated compared to Aram. I only found two units that were post-dating the collapse, and they are the Lighton layer unit and the cap unit. So as you can see in panel B, the Lighton layer unit is overlying the bedrock through an unconformity, and then on top of the Lighton layer unit, we have another unconformity and the cap unit. These two units are very different from each other. So the Lighton layer unit has high albedo, a fine bedding, and it's very prone to erosion. As you can see here on the right, it's eroded in a very peculiar way. While the cap unit has a more massive appearance. It appears to be a monostrata, and the albedo is lower, and it has a rugged surface. But the fact that there is an unconformity between these two non-disrupted units is telling us that something happened. between the deposition of one and another. And then after identifying all the units, I moved to the structural observations. I found a lot of faults, grabens, and I found also some patterns, radial and concentric patterns, and also a variety of other features that in literature are often interpreted as related to volcanotectonic activity, such as the pitch chains. And there were some areas where the pitch chains were so dense that I couldn't map them at that resolution, at that scale. So as you can see here in panel D, I just mapped the area and I called it densely pitted area. So my feeling was that the volcanotectonic prevalence of the evidences was telling us something, and maybe about the origin of this collapse. And then it was time for some spectral analysis. And I was very lucky because right at the contact between cap unit and light on layer unit, there was a crescent cube. And I was super excited. I was like, okay, this is a jackpot. I'm gonna understand everything about these two units. The first thing I did, of course, was to try some summary parameters. And in C here, you have the RGB for chlorides. So blue is supposed to be chlorides and yellow, other hydrated minerals. Now, I don't believe that all this blue is chlorides. This was also a very dusty area, and the blue is right in correspondence of this dust. But look at the light on layer unit. It's purely yellow. So yellow means hydrated minerals. And this was, I was very happy about it because everything was consistent so far with what was observed in the other chaotic terrains. But then I got to the spectrum. And I did many attempts to find the right region of interest. I did different ratios, but I couldn't really find a pixel where the spectrum was good. So you can see from the spectra that there are lots of noises, the absorptions are narrow, and they don't allow a proper classification of the mineral. I had some absorptions around 1.9 micrometers that are typical of hydrated minerals, but it was not enough to classify what mineral in particular. So I was very sad about this, but I didn't give up and I was looking for other crescent cubes. I found one that's actually in our own chaos. You can see it here in the top right angle of this image. And that was just to confirm the basaltic nature of the bedrock. But the interesting one is this cube in the northeastern periphery of Arsenos chaos. What I found here was a deposit that you can see in the panel A as greenish, light green, and it was just in correspondence of a volcanic graben, surrounded by all the basaltic plateau. And in this case, the spectra was very good. The summary parameters were good as well, and I was able to determine that probably it was smectite. Smectite is a particular type of phyllosilicates that could be the result of a hydrothermal alteration of basalts. And if you combine this information to the fact that it's occurring right in proximity of this volcanic graben, my hypothesis is that this was relatively small hydrothermal environment. So at the end, I came up with my morphostratigraphic map. You can see in warm colors the volcanic units, so the chaotic terrain subunits, and in warm colors. And in cold colors, the sedimentary deposits, so the cap unit and the lateral layer unit. And even though I wasn't able to classify specifically the mineralogy of these two units, by analogy with other chaotic terrains, and because I had some minor information about hydrated minerals, I decided to interpret them as sedimentary. And I also mapped all the fractures and the craters and so on. But this map led me to question, the origin of this collapse, because what I found was mainly volcanotectonic evidences. I also found a very nice lava flow that I didn't show you because I think I'm already running late, but there were many evidences for volcanotectonic activity, the pitch chains, the volcanic grabens, of course, the lava flow, and very few hydrated minerals and no morphological evidence at all for example, fluvial deposition or erosion. So I started to think maybe this collapse was actually just volcanic in origin. And I'm not saying that water was not there, that there wasn't a cryosphere, a permafrost. I'm just saying that the primary trigger, maybe it was volcanic. And also we have that hydrothermal area just nearby arsenic chaos. Very widespread basaltic mineralogy. As for the post-collapse units, unfortunately, I couldn't classify the minerals, but since they don't have any volcanotectonic feature and they're not affected by the faulting, we can safely say that they're post-collapse. But this is the idea that I had. I figured, what if there is an underlying magma chamber and it's undergoing multiple cycles of inflation and deflation. This is a particular type of caldera collapse that's called chaotic caldera collapse. Now, I don't know if this is a case, but I had this feeling that maybe this could be the answer. These multiple cycles of inflation and deflation generate polygonal blocks. So that's why I decided to perform the experiment in laboratory. And then in a late stage, we would have the hydrothermal alteration and deposition, the lava flow. And after the magmatic activity was over, we would have the emplacement of this aqueous environment, either lacustrine or evaporitic. I can't say that because I couldn't classify the minerals. So that's how the experiment started. The cases of study were still arsenic and pyrrhic chaos. These are all the volcanotectonic evidences. You can see also that the grabens often have a Y-shaped conjunction that's characteristic for inflation. This is something that I didn't say before. And also I added a couple of floor fracture craters that, as I said before, are very similar terrains, and one was on Mars and one was on the Moon here, Commonwealth crater on the right. And this is the setup of the experiment. We have a rubber membrane that was simulating the magma chamber, and polyglycerine simulating magma. It was introduced into the magma chamber through a syringe pushed by a piston. And then after pushing inside the polyglycerine, we would withdraw this polyglycerine. And in this way, we were simulating, the inflation and deflation cycles. On top of the magma chamber, we put some very fine grained sands, the brittle material, to observe what fractures this inflation and deflation would generate. And this is the results. So we performed two experiments. One had rounded magma chamber and one had a bean shape resembling arsenic chaos. And in both cases, the results were surprisingly good, because they were not good just for the qualitative aspect. You can see this pattern of radial and concentric faults that intersecting each other generate the polygonal blocks, and that's very consistent with what we observe. We have the ring fault, which is the most external normal fault, and we could identify all these features also in the natural cases, but also quantitatively, the measurements were fitting with the natural cases. So this was actually a great success for me, because this idea was born like, I had this flashback of something that I studied in geology when I was a master's student. And it turned out that, maybe this could be the actual trigger for the collapse of chaotic terrains. These are other measurements. So lessons learned and take-home messages. After all, these chaotic terrains are not so chaotic. It was just about, being confident with them and find a pattern. What I observed was a majority of volcanotectonic evidences. Very few aqueous evidences. In this case, I repeat, in iron chaos, the situation is a bit different. And after the collapse, we would have this aqueous environment with the deposition of evaporitic, maybe, deposits. Chaotic terrains are very similar to floor fracture craters, so maybe we should focus more on why are they so similar. Maybe they share a common origin. They have the same patterns of polygonal blocks. The angles between these faults that are bound in the polygonal blocks are consistent. So yeah, maybe they could have a common origin. And I think that our experiment was a very nice proof of that. And with this, I finished. I think I'm on time. So thank you very much for your attention. And I hope this helped for your practical activity later on.
Thank you, Erica. This was very, very interesting. Sorry, my webcam never works properly.
Thank you.
So we have time for a couple of questions. We have one asking, could this formation mechanism also be used to explain the fractures in Enceladus craters, so icy surfaces?
I wish I could answer that, but I've never took a look at Enceladus, so it would be wrong of me to provide an opinion without actually knowing the topic. But I mean, this caldera collapse was studied before me. There is a paper from Troll, and they found some calderas on Earth, and they believe they were formed with this caldera collapse. So if they were found on Earth, and I hypothesized that this could be the same mechanism on Mars and maybe on the Moon, yeah, it could be a formation mechanism also for other planetary surfaces. Why not? But I can't go into detail with that because I don't know much about Enceladus, unfortunately. I'm a Mars person and Moon.
Okay, then we have another question. Could you repeat the meso's evolution in other terrains? So the other mechanism of meso's evolution.
Do you mean the erosional evolution, so the transition between mesas and knobs?
Yes.
Yes, okay. Yeah, this is actually still not clear, and it was not investigated by many authors. I mean, we all assume that that's the basaltic bedrock, and for some reason, in some parts, it's more eroded than in others, but there isn't really an explanation for that yet. Also, well, maybe with additional spectral data at high resolution, we will be able to, classify better the single parts of the bedrock in chaotic terrains. But for now, there are not so many prism cubes, at least in arsenoscales.
Okay, we have another question. What was the formation timescale on the smectite hydrothermal areas, and how common are those?
Sorry, I was reading another one. Formation timescale on the smectite. Smectite deposits are very common on Mars. It's one of the most common minerals. But when you find smectite, you don't only look at, at the mineral itself. You have to think about the geological context. So if you find smectite in a deposit with lots of other phyllosilicates and particular geomorphological features, then you can hypothesize something. The way I found the smectite, it was just isolated and pure and close to these basaltic plains and volcanotectonic graben. So this is a very particular case compared to the others, to the other deposits of smectite.
I think we have time for one last question. So how one could distinguish regular knobby terrains from a high thermal inertia ones without thermal inertia dataset? Anticipating this afternoon practical.
That's a smart question. Well, the simple answer is you can't. I mean, you can't be sure without the thermal inertia data. But what I observed, at least in arsenoscales, is that the high thermal inertia chaotic terrain subunit is a bit more eroded than the knobby terrains. So it's really remnants of knobs. So this could be helpful, but you have the confirmation only with thermal inertia data sets. So